it's important for us to understand how atoms come together and how atoms interact with each other to do things like form molecules. How atoms interact with each other can affect the properties of the molecule, how it undergoes reactions, and all of that's very important to how processes run in things like living systems, like a plant or a human. And at the basis of all this is chemical bonding. And so just to get a foundation as to how atoms interact, we can start with a little discussion on chemical bonding. And a little analogy will really help you with this. So let's say you're sitting on a first date with someone and you're going to watch a movie and share a bucket of popcorn. Now, when we hear the word sharing, we think sometimes, oh, one person will get half of the popcorn or 50% of it, and the other person will get 50% of it. And yes, that is sharing. That's beautiful sharing. It's perfect sharing. But wonder if your date got 75% of the popcorn and you got 25%. Well, that's still sharing. It's just unequal sharing. Where the first scenario was equal sharing, that would be unequal sharing. Or wonder if your date got 100% of the popcorn and you got none. Well, that's not sharing at all. They actually got everything. And this is important because you have to decide at this point whether this is someone you want to keep seeing. Although I won't answer that or discuss that aspect of sharing of popcorn and how it can build relationships, it does give us some insight into what we know as chemical bonding. But when it comes to chemical bonding, it's not people sharing, it's atoms. Atoms such as carbon or nitrogen or hydrogen or any of the ones on the periodic table. Sometimes you can be shared between same atoms and sometimes they can be different atoms. We also have a difference here when we're talking about chemical bonding. It's not popcorn we're sharing, it's electrons. Remember, electrons are outside the nucleus of the atom. They're kind of flying around the nucleus of the atom. And so these are the ones that these are the subatomic particles, the electrons that will be sharing between atoms. Now we can separate bonds between atoms into three major categories. And these three categories really just indicate how much sharing or what kind of sharing is happening of the electrons between the atoms. The first kind is nonpolar covalent. In a nonpolar covalent bond, the electrons that are being shared by the atoms are being shared equally. This is like you getting 50% of the popcorn and your date getting 50% of the popcorn. It's equal sharing. And an example of this is a carbon-hydrogen bond, for instance. That is a nonpolar covalent bond. A polar covalent bond is when you're sharing the electrons, or the atoms are sharing the electrons, but they're not sharing quite equally. This might be like 75% to your date and 25% to you. And so this bond is not equally shared, but it's still shared. And so an example of that might be like a nitrogen-hydrogen bond. An ionic bond is one in which really there's no sharing at all. One of the atoms got all of the electrons and the other one didn't get any. And this is something like NaCl. We might see that as an example of an ionic bond. Now, how did I know that? How did I know that a carbon-hydrogen bond was nonpolar or a polar covalent bond was NH was a polar covalent bond or NaCl was an ionic bond? For that, we have to use what's called the electronegativity chart. This is a picture of the electronegativity chart for all the atoms on the periodic table, or all the atoms known to man, essentially. And if you look at that, it shows on the electronegativity chart, it shows the atomic number, which is the number on top of the letter or letters, and below it is the electronegativity number that we're going to be using. And so this is a nice chart because it gives you some information that we can utilize to understand how any two atoms would quote, share the electrons between them. Now on this chart, I highlighted, or 6 of them are highlighted in blue. These are the major atoms in organic chemistry that you will see. Not that you won't see any of the other atoms, but these 6 are the major ones. You're going to see in molecules carbon and hydrogen and oxygen and nitrogen and phosphorus and sulfur are the major atoms that you see in a lot of organic molecules. And so I highlighted those, but again, you can use this chart for any of them. But with that, I want to focus in on sort of just the top part of this chart and kind of make it so it's a little bit more visible for us. So here's the same electronegativity chart, but I've cut out a lot of the atoms or elements that to focus on, just the ones that are important for our discussion now. You can use any 2 atoms. What's cool about the electronegativity chart is you can look at any 2 atoms and know how they'll share electrons between them by using the electronegativity chart. You'll know if it's equal sharing, not equal sharing, or just one of them got all of it. And to do that, we're going to go ahead and give it a whirl with the practice one. And let's go and I'll kind of look at that. Let's look at the NaCl bond. And we're going to ask, okay, if those 2 were to interact and share and have electrons, how would they share them? And so what you do is you go on the electronegativity chart, and I can see sodium is right here, and chlorine is over here. And notice that sodium has a 0.93 number as its electronegativity number, and chlorine is 3.16. Now, for our discussion, it doesn't really matter what those numbers really mean empirically, like what does 3.16 really mean. What we care about here is this is going to tell you how well they attract electrons to them, how many of them they'll take. The bigger the number, the stronger the attraction of those electrons. So what we're going to do is determine the difference between these 2 values, and we only care from a positive perspective. There's no such thing as a negative. So what we're going to do is we're going to take 3.16 and subtract 0.93, and what we get here is 2.23. The difference between those 2 atoms and their electronegativity is 2.23. Okay, great, we can do the math. But what does this number mean? Well, it's been figured out that basically if the number is greater than 1.6, it's an ionic bond. If the number is 0.4 to 1.6, it's polar covalent. And if it's less than 0.4, it is nonpolar covalent. So I'm running out of space there. And so we look here and we can see that the number we got difference between them is 2.23. That tells us it's an ionic bond. That's a big number. It's greater than 1.6. And you probably know this from Gen Chem. That's an ionic bond. You knew this was ionic. But now we can see how we can calculate that to determine if it is ionic or not by using the electronegativity chart. What it also means, the electronegativity chart can also tell us which atom gets most of the electrons, and it's the one with the bigger number. Because chlorine got all of the atoms, or all of the electrons, and remember electrons are negative, that's why we put a negative next to chlorine. Because sodium lost those electrons because chlorine got them, we give sodium a positive charge. And so in an ionic bond, one of the atoms is negatively charged and one of them is positively charged. Sometimes it's a +2 or a +3, and that has to do with how many electrons they're sharing, or not even, quote, sharing. They're not really sharing anymore. One of them's getting them all, and that tells us how many electrons were transferred from, in this case, sodium to chlorine. And in this case, 1 electron is transferred. In this discussion, we're not going to talk about how many electrons are transferred and all that. We can just tell that in this discussion that we can tell that when sodium and chlorine try to form a chemical bond, they can, and the chemical bond they form is an ionic bond because we use the electronegativity chart to tell us that. Now, just for reference, you can find an electronegativity chart online just by typing into Google electronegativity chart and show images, and you'll see whole bunches of electronegativity charts. You can use them, and they all pretty much work the exact same way. And you can use that electronegativity chart to determine what kind of bonding is happening between 2 different atoms. Now, let's try it out for a carbon-hydrogen bond. So that was one I told you was a nonpolar bond. And so there's our carbon-hydrogen bond. Now, one thing to note about covalent bonds. In organic chemistry, you're going to see way more covalent bonds than you are going to see ionic bonds, so this is probably a little bit more important. But when you see a bond, a straight line, put an arrow to it, that line sitting between carbon and hydrogen, that's indicating a covalent bond. And what that represents, or another way to represent it, is by putting the carbon and hydrogen with 2 electrons between them. That bond, that line between carbon and hydrogen that you see in the top, is the same as what we see below, showing instead of a line, we show 2 dots. And those 2 dots represent electrons. So anytime you see a covalent bond shown as a line, that's representing 2 electrons, just to kind of make sure we're aware of that. So I can represent it either way I show on here, that carbon-hydrogen bond, but more often you're going to see it with the line between them, not the 2 dots between them. So there's a carbon and hydrogen molecule, and so what we can do is determine what type of bond it is. I've already told you what it is, but let me show you using the electronegativity chart. Carbon is 2.55 and hydrogen is 2.20, and when I do the math there, I get 0.25. If we look on our previous slide, we'll see that that falls in the less than 0.4, and that's a nonpolar covalent. So this will be a nonpolar covalent bond because it's less than 0.4. The difference in electronegativity between them is less than 0.4, which means they're pretty much equally sharing. Are they perfectly equal sharing? No, they're not. For perfect equal sharing, the value between them would be 0. We're a little bit, this is almost like one person's getting 52% of the popcorn and the other person's getting 48% of the popcorn. That's pretty close to equal sharing. Not quite enough where it's starting to become unequal sharing. We'll still call that equal. Remember, there's a continuum, essentially, of differences in electronegativity between atoms, right? Some are going to be 0.25. We might be able to find some that are 0.4, 0.7, 0.9, a lot of them. And so we just have cutoffs, like sort of cutoffs being the 0.4 and the 1.6 being the cutoff for classifying them as nonpolar covalent or polar covalent or ionic. But realize there's a continuum there. So it doesn't have to be exactly 50-50 to be considered nonpolar. They can be slightly different in electronegativity, but still be classified as nonpolar. And the reason is because chemically, this bond, carbon-hydrogen, acts very nonpolar. It acts like they're equally sharing, and so that's why something that has a 0.25 difference is a nonpolar bond. If we look and move on to a nitrogen-hydrogen bond, we could do this one more time. Nitrogen off the chart is 3.04. Hydrogen is 2.20. If we subtract them from each other, we get 0.84 if I've done my math correctly. And looking at the little chart tells me if it's over 0.4 but less than 1.6, which this one is, this will be a polar covalent bond. Now, an important thing to know about a polar covalent bond is the electrons are not being equally shared between the 2 atoms, but it's not like one of them got all of the electrons. And remember, electrons are negatively charged. So the question here is between the nitrogen and hydrogen, which atom gets more of the electrons than the other one? For instance, like you and your date sitting there sharing popcorn. If there was a 75-25% split, we know it's not an equal sharing of electrons, but there's still sharing there. Who got more? Was it you or was it your date? Well, in this case, who got more, the nitrogen or the hydrogen? And again, it's the one with the bigger number is the one that got the more of the electrons. So nitrogen is getting more electrons, which means it's kind of a little bit more negative. Remember, in an ionic bond, NaCl, chlorine got all the electrons, so it was negatively charged because it got an electron, and sodium gave up an electron, 1 electron. In this case, nitrogen's getting some of the popcorn, but not all of it. And so how do we show that? We know nitrogen is going to be a little bit more negative, and we show it with the Greek symbol delta. Whoops. We show it with the Greek symbol delta, which looks like that, with the negative charge over nitrogen. That's different than the whole negative charge on chlorine. The hydrogen is going to be then kind of positive, a little bit different than sodium, which has a full-on positive charge. So when you see that delta sign, that means partial negative and partial positive charge, where sodium chloride is a full-on negative charge and a full-on positive charge, -1 and +1. You can think of nitrogen and hydrogen in our polar covalent bond as being kind of like plus 0.5 and minus 0.5. It's not a, it didn't get, the nitrogen didn't get all the electron, it just got some. It got a little bit more than the hydrogen. And so those partial charges shows us which one got more of the electrons, or which one's getting more of the electrons than the other. Which got 75% of the popcorn and which one got 25% of the popcorn. And you got to remember that electrons are negative, so the one that's getting more is the one that's going to be negatively charged. Now why don't you give it a try? Here's 4 sets of atoms, and I want you to determine whether that is a they will create a nonpolar covalent bond, a polar covalent bond, or an ionic bond. When you're done, just restart the video. Go ahead and pause it, but when restart the video, and then I'll walk through the answers. So for carbon and chlorine, what we have there is chlorine is a 3.16. I'm going to subtract carbon, a 2.55. And again, it doesn't matter if this difference is negative or positive. That just depends on how you plugged it into your calculator. You're just looking for the absolute value. So I always just take the biggest number and subtract it from the smaller number. And when I subtract these two from each other, I get a 0.61. And that is a polar covalent bond. So I'll just put PC out here, polar covalent. On the second one, we have H and F. F is the bigger one, so it's going to be 3.98, and H is going to be 2.20. And so for those, we subtract those from each other, and we're going to get 1.78, I believe. I think it's 1.78. That's a big number, so that'll be an ionic bond. And just so we know, I know which one will get the electrons. In this case, F will get the electrons, and so F will be negatively charged, and the hydrogen would be positively charged. An ionic bond is going to be a full-on charge. Again, we're not getting into how many electrons will be transferred. In this case, it would just be one. The carbon and the chlorine had the bigger number, so it would get, because it's a polar covalent bond, a partial negative charge, and the carbon would get a partial positive charge, because the 2.55, which was the electronegativity of carbon, is less than the 3.16 of chlorine. Carbon and carbon, it's the same number twice, so this one's a pretty straightforward one. It's 2.55 minus 2.55, and when I subtract those two, I get 0. So this is a nonpolar covalent bond. Because it's nonpolar, neither of them are charged in any way, so I don't have any charges to them, not a partial charge or a plus or a minus. In fact, because it's 0, it's equally charged between them, or the equal sharing between them, almost like a 50-50 perfect split. And in the last one, notice it's a carbon-carbon double bond to oxygen. If we put that with electrons, just so you know, it would be 4 of them would be shared, because I have 2 of those lines, or 2 of those covalent bonds shown, not just one. Every line represents 2 electrons. I have 2 lines between them, so that represents 4 electrons that those 2 are sharing. And when we share those 2, it doesn't matter if it's 1, 2, 3. It doesn't really matter at all. You still do it the exact same way. And so in this case, it'd be 3.44 for oxygen minus 2.55, if I have that correct. 3.44 minus 2.55, and I'm getting 0.89. That's above 0.4 and less than 1.6, so that's a polar covalent bond. and I know which atom is going to get the partial negative charge, because polar covalents have partial bonds, or partial charges, not covalent bonds, partial charges. Covalent bonds are the same, and so the oxygen's partial negative, and the carbon's a partial positive. I hope you like this video. If you're looking for more videos just like this, check out my channel and continue to look at some videos in there. I'll be populating with more organic chem videos to come.